All right, good afternoon. My name is Tyler Jewell. I'm CEO of Akka. Akka is a 16-year-old company. We were previously a development toolkit for building distributed systems. It's been downloaded 1 billion times. There's over 100,000 systems that have been built with Akka. And on any given day, 2 billion people touch an application that is powered by Akka underneath the covers. And today we're going to do a little journey and have a discussion about what is agentic AI and what's the direction of it. And that's an interesting question. What is agentic AI? And it's an interesting question to explore. And we need to explore it because the productivity gains that are being witnessed are absolutely stunning. Over the last 6 years, if you take a logarithmic curve of all the models that have been released and plot them, every 7 months, the capabilities of a single request, call it an agent, call it an LLM, have doubled every 7 months in the last 6 years. If we're able to sustain that pace of innovation over the next 6 years, in 2030, a software engineer who uses an agent will be able to complete a month's worth of work on a single request. It's a stunning, stunning change. 6 years ago, we got a couple of seconds worth of effort through autocomplete, and now we're looking at a complete month's worth of software engineering work. And, you know, work, magically, there we go. So how is this happening? Well, the first thing is, let's break this down and, kind of understand what is agentic AI. The first thing we need to understand is that LLMs are not perfect. They're stochastic engines that generate random outputs. They're highly probable random outputs, but even today, if we take a look at the most expensive models with the largest context windows that can handle do the most processing, they're only in the 76 to 82% accuracy range, which, flip side is that that's an 18 to 24% failure range on every request that you give to it. So the first thing you have to understand about agentic AI is that the things that you're working with are randomized. This is not going to work well. Here we go. All right. The next thing is that when you look at an agent, you have to recognize that it's a system. It's actually something that is working with data. That data is interacting with that LLM over a network. So you've introduced a network. You've introduced data. It is a system. An agent and an LLM is a distributed. Is it a distributed system? I wouldn't quite call it that, but it is a system. And because it's working with data, it's going to be stateful as well. And an agentic AI system, the agent itself, if it wants to have some remembrance of the previous execution, that's called memory. And memory, therefore, is a database. You got to have some sort of mechanism of persistence that the agent can tap into, and that suddenly makes the agent stateful. And this stateful behavior extends beyond the agent because you have heard about people talk on orchestration or workflows, and we'll discuss a bit more of that. But orchestration is effectively a fancy way of saving the call stack after each step. So that requires persistence as well. So we have random LLMs, we have a system, and it's stateful. Furthermore, if you just didn't want to add some more complexity to this, is that it's been shown that the larger your context window, the bigger the prompt you give, the less accurate the response is going to be. It's called context rot. Right? So unlike databases where as the transaction volume runs higher, you get a very deterministic and consistent profile, with agents, as the memory gets larger, if you insert that larger and larger memory without trimming or managing that context window, your accuracy goes down. So you've just increased the randomness profile just by using the LLM. So when you're dealing with agentic AI, you have to kind of accept some of these elements that you're dealing with, and you have to change your mindset. Over the last 30 years, with most of the systems that we built, we approached them from a determinism point of view, that we could design systems that had rare failures. If you do that and you try to put that into production, you are going to have an unhappy outcome. And really, what you have to do is you have to recalibrate yourself and accept that all you can do is strive for perfection, because that these systems will never achieve the expected outcomes that you have, but you can strive for perfection. And striving for perfection is important because how do you strive for perfection on a system that's continuously adapting, continuously changing on you? And so when we deal with enterprise accounts who are looking to put agentic AI systems into production, they start by assessing their risk profile. And what they realize is that historically, with most of the systems that they had to assess, it was purely a systems risk. Things related to resilience, availability, performance, SLA management, perhaps some cost management, isolation, security of the network. But because of the randomness of the LLM and emergent AI, which we're going to talk about in a second, and context rot, you also have to factor in that there's a randomness risk. And so your risk profile has expanded. Systems risk and randomness risk. It really disturbs and bothers a lot of the enterprises that we work with, not just the context risk and the randomness risk, but the emergent AI. Emergent AI is I guess a concept that came out in April of this year through scientists, and it shows that if you take an aligned AI, and an aligned AI is a model that has been not only tuned, but all of its ethical and moral safeguards have been validated, and then you put that into production, you can retrain that model or feed that model with prompts and information that you give to it that distorts its understanding of truth. And as it goes on over time, an aligned AI that had ethical safeguards can be turned into a malicious AI that almost has no safeguards whatsoever. So you can convince the AI that its reality is different than what it was programmed to be. So all these things are factors that affect your risk profile in order to get an agentic AI system into production. And so it's no wonder that if you've paid attention to the news, that people tell you that 95% of AI projects fail or that they fail to make it to production. A lot of that stuff is experimentation, but most of it is enterprises coming to this sort of stark reality that there's three problems that are keeping them, three barriers that are keeping them from entering into production. The first is that these systems are complex, because they are distributed systems. There's distributed state for your memory. There's orchestration for managing them. They are operating over a network. And on top of that, they're going to be constantly changing. And then most importantly, they're just not trustworthy. You don't trust them. Now, people default into, hey, it crashes, or maybe it's not the most reliable framework, and that's certainly a concern. But there are safety and ethical concerns that get in the way of people moving these things into production. And then the cost factor. Everybody's aware of how much it costs to consume an LLM, but in an agentic AI project, the costs go much further beyond that, because there is a nurturing and ongoing maintenance of the agentic AI system that is continuous. And some of the compute and infrastructure builds that go into the management of the agentic AI tier can equal or match the cost of the LLMs themselves. So complexity, distrust, and cost are these real barriers that move forward. And so the bottom line though, is that if you do not trust your agentic AI system, it's not going to go into production, And even if it does go into production, it's not going to stay there. Right? And I tell this to our prospective customers all the time. If we can't get your system into production, we're not going to make money because we only charge for production usage of our system. So our mission, and I would argue that the definition of an agentic AI system is, one, that a method by which you are going to infuse your applications with AI, right? We want to build applications that have AI in it, but it's also a system that continuously builds trust. If you don't have both of these components, it's not agentic AI. Now, I mentioned before that we talked about how there is no such thing as perfection. There's no such thing as determinism. So all you can do is you can strive for perfection. How do you strive for perfection in a computing system? It's one that continuously adapts. It's one that is observing its environment, and it's striving to be as close to perfection as possible. And when you do that, then you can have trust. So there are 6 steps that we talk about with our enterprise accounts on how you go about building this framework of trust. Usually, with a lot of systems that you build, you end with governance. You think about observability, the metrics, the policies, the controls that you want to have in place after you've designed the system and built it. Well, since this system is an imperfect beast, it's never going to be fully accurate, you have to invert that. You have to start by understanding what your boundaries are going to be, what your metrics, guardrails, protective controls are going to be in place, and how you're going to measure these things and observe them. So you start with AI governance. You don't end with it. Right? You don't build the agent first and then figure it out. The next is that every agentic process needs to run in an impenetrable runtime. It needs to be fully isolated. And then the network that it's operating on must be a zero trust network with least privileges and mutual TLS connectivity. The system has to guarantee resilience. And in order to guarantee resilience, you have to be able to guarantee that there's never going to be any data loss of the memory that the agent's consuming, and then therefore the data that is going to manage that orchestration. So it has to be able to recover, not only locally, but it's got to be able to recover over territorial zones. Agents, by definition, are stateless processing units. At the most basic level, they're just a compute unit, and you have to be able to assign a verifiable identity to those agents. Because the agent is going to interact with other LLMs, and it's going to interact with other agents, and it's going to interact with other APIs and other tools. In order to do that on a safe basis, it's got to be able to identify itself. It needs to be able to verify that identity, whether it's taking that identity from another system or the user that's engaging with it, and be able to pass that identity along. And you have to then be able to trace every interaction across this distributed system and put it into an immutable, irrefutable audit log. And only then can you have true chain of thought and traceability that leads to an explainable outcome. And explainability is a critical part of these systems, because if you don't trust it, right, you then need to have explanations for every decision that was made from the beginning of time. And then, because it degrades over time, it has to continuously adapt to its environment. It has to be able to read those environmental sensors, take the events, get learnings either from reinforcement learning of the models or other places, and incorporate it all so that the system gets a little bit better on each iteration that it goes. So Akka, we used to be a development framework. Now we ship an agentic AI platform. This platform is everything that you need to build an agentic system and get it into production quickly, keep it there safely, and we can guarantee that it's going to scale more cost effectively. So much so that we are consuming up to 95% less cloud compute than certain Python frameworks that you use, like LangChain and LangGraph. There's reasons for this. And so our mission is to help you build systems that never fail, but also continuously build trust. Now, we have an SDK. This SDK includes everything that you need to build, test, and run an agentic system. And what makes us different is that we approach it as a system, not as a piece part. So you build the entire system with the SDK. You test the entire system with the SDK. You package it. You deploy it. And then when you run this, we run this as a cluster. And I'm going to talk a little bit about how we guarantee resilience and elasticity. But that cluster can then deploy into any environment you want, on edge, bare metal, onto Kubernetes. And then we provide a whole series of manageability utilities for various audiences so that you can build trust into that system and make sure that it's behaving exactly the way that you want. Distributed systems, which is what Akka is incredibly well suited to this entire problem space because a distributed system has always started from a first principle of not trusting the environment around it. We always assumed that the hardware could fail, that the network could be disruptive, and that the system needs to self-heal and adapt to those changing conditions. Well, an LLM with its randomness is just another variable that we don't need to trust and adapt to. Granted, it's a content type of randomness. It's not a hardware or a network, but it's just another form of randomness. And so a distributed system is well suited to solving the agentic AI problem. So how do we do that? The first is we can guarantee elasticity. We do this because at the heart of Akka is a form of concurrent processing called actors. Actors are a lightweight form of compute, about 4 kilobytes in size. We can get hundreds of millions of concurrent actors on a single core. And by doing this, actors also have an isolated structure with supervisors. It's almost as if they are running their own agentic system, but supervisors can spawn actors. It can change the flow of information between those actors, and it orients the system so that whatever the goal that it was assigned to, it can run it in the most efficient way using the maximum amount of resources that have been allocated to it. And we do all this in a way where you can build Akka clusters that run across millions of nodes, and by doing that, you can get fan out, fan in, and then traffic steering routing for your end users, allowing you to have the maximum amount of compute processing for your end users against whatever physical allocation that's been given to you. We also guarantee resilience, and this resilience can be for your agentic memory. It can be for your orchestration, your durable execution. It can be for just memory objects that you create, or even the streams that you have within it. And the way that we do that is all your state is tracked as a sequence of events that's put into an event journal. That event journal is persisted transparently to the developer behind the scenes. But because you have a sequence of events in any sort of disruptive environment, Akka automatically can go to that journal and rebuild your agent's memory instantaneously so that it can recover exactly to the state that it was at previously. We do this for your agent memory, for any objects that you create in the system, and it's a form of event sourcing. And we've been doing this for a long period of time. It's one of the original foundations of what Akka is. But we then evolved all this into what we now have is domain integrated context engineering. It's called DICE, which is designed to help eliminate and erode that context rot. And it's effectively a way of allowing your agents to view the domain object that you have, the application behavior, as a form of tool so that your agents can interact with the rest of the system as if it was like a remote MCP server. And when you do this, your context window shrinks and the appearance of rot goes down quite significantly. And then last, we have streams. And streams are a form of real-time processing that takes audio, video, metrics. It could be events from a pub sub broker like Kafka. And it offers a form of continuous processing so that you can take all your environmental sensors, process it, synthesize it, update your memory, update your context windows, alter the goals that a orchestration has, and all of that then affects the next iteration of the system that it runs. And then finally, for our larger enterprise accounts, we bundle all this up into multiple regions. And you can deploy Akka clusters into different regions. And when you do that, you can deploy the same agent into 2 different locations. And then they have a form of active-active replication of all their state between those regions. And because it's active-active, you can lose a whole region, and then the system will fail over and offer continuous operation on the failover region. And when that downed region comes back up, there's a disaster recovery and a reconciliation of all that state so that the system carries on. We have customers that are deploying into upwards of 30 regions, and they use those regions not just for high availability and continuous operation, but also for data sovereignty and cloud sovereignty. These regions run in any different cloud provider, so it could be Amazon, Azure, or AWS, and you can actually do high availability and disaster recovery across cloud providers automatically. We've been now working on the AgenticAI problem for about a year. We have about 45 accounts that are in production, and we've started to see some really remarkable performance metrics. Our largest account is deploying about 18,000 cores in a giant cluster, and they're processing more than 5 billion tokens a second through the system. It's about 1/20th the size of OpenAI on a tokens per second basis. And in that particular case, what they're doing is it's using a feedback loop because they're processing real-time content streams about users, their advertisers, in order to generate recommendations through a series of a half-dozen different models. And this turns into a giant feedback loop that then ultimately leads to recommendations and personalization that goes out the door. Some of the things that people use to build these agentic systems, they're doing large data pipelining, where there's large volumes, like petabytes worth of documents that need to run through massively concurrent pipelines. We have vendors who are doing customer support and chatbots. There is traffic routing optimizations that you can do with modeling. And so it's some combination of 6 nines of availability, large numbers of concurrent end users, very low latency issues with your memory, or you've got some sort of territorial, multi-jurisdictional deployment requirement, and all those things come together into the customers that we have landed here. I am going to have another session at I think it's about an hour, and I'm going to do a live demo of building some multi-agent systems and deploying that into clusters. And I think we're going to do that in this room. But until then, me and my group, we're exhibiting. We'd love to talk to you and answer any of the questions that you have at our booth. Other than that, thank you, and welcome here.
Thank you. If anybody has any questions for Tyler? No? Oh, sure.
Thank you, Tyler. So I'll start, so basically, what's amazing to me is like there is a huge scale of these requests. So what kind of, it's a distributed system, like what AI features, right, these clients want? What are they bringing in from the Python world? How do you see the stack around Akka emerging on top of Akka?
So that was 2 questions in one. It was, what are the features of Python that people want, or AI features of Python that people want, and then what's the future here? The interestingly thing, I'll say that the Java stack right now, there are like 6 or 7 agentic AI frameworks in the Java space, and they are matching pace with LangChain in terms of capabilities on the AI front. The big things that are really necessary in a system like this, you got to have guardrails. Guardrails are a form of being able to validate inputs and outputs, and then being able to interrupt your control flow. We've got that. You got to do evaluation. Evaluation is a way of evaluating the accuracy, safety, and performance of the system. So we provide it's actually a really cool way to do it, but it's an LLM as a judge approach where the system can be running, and then in parallel to that, you've got these other agents that are evaluating the first one that's running, and then as the agents are evaluating it, they're generating events that affect the system itself, and it just keeps going in a kind of an LLM as a judge evaluation framework. The way that you do immutable tracing, you're going to see some really cool stuff, but you've got to be able to trace not just the interaction between the LLM and the tools and whatnot, but you've got to be able to follow the trace from the API through the distributed system all the way, and it's got to be tamper-proof. You have to be able to demonstrate tamper-proof. And then the number of security things, we just finished an RFP. It was a 300-page request just on the security dimensions on AI. And so AI introduces a whole different kind of risk profile that traditional systems don't introduce, and you have to demonstrate an ability to either prevent or resist all those issues.
Questions?
Thank you for the great presentation. I'm right here.
Yeah, thank you. All right.
Great presentation. Although most of the technical details I would have many different questions over, but I particularly liked the 5 billion tokens per second metric. Can you share some tricks and tips on how you're able to support that kind of load? And would it mean that you would have to keep a lot of open connections? Like anything that you could share from a distributed systems point of view?
Yeah, so that's 5 billion tokens a second, and that's an 18,000 core system. Our largest deployment it's non-AI, but our largest deployment is 300,000 cores. And that is one of the world's top 4 observability vendors in all the data ingest that they do on that. So, so what are some of the principles that you got to get into in order to be able to get to that level of scale? Everything needs to be non-blocking. I mean, everything, all requests through and through, not just the initiating end user requests, but also all the services within Akka, because you've got workflows talking to memory, talking to agents, talking to streams. Those all have to be non-blocking, actor-based concurrency mechanisms. And then the outside resources that you're talking to need to also be reactive. Most model systems are not reactive yet, meaning that they're going to be synchronous and blocking connections, and so you're going to have to manage against that. But I don't think it's going to be long before we see reactive drivers for LLMs, inference providers, and whatnot, and that'll help with the scalability of it all. The systems that don't scale as well, it's not about the number of concurrent activities that are going on, it's about the amount of state. So if you want to have a stateful system and you want to have petabytes distributed around the world, that's where it becomes more challenging. And we can talk about that at our booth on how we do that.
Great. I guess we have time for one more question if anybody has anything. Yeah. No? Okay, so yeah, it's 2:10, so it's like right on time.
Awesome, thank you.
Thank you.
All right.
Thank you, Tyler.